Okay, let's start. So any questions that remain before we start? I want to start all over on junctions and kind of, yeah. So any questions from natural transformations or functors? Okay. So the next thing we're going to talk about is junctions, which we already started. And junctions and monads are very similar things. And there's a talk all about junctions on Saturday at 11:30. At 11. So if you want to hear more about junctions, there's a whole talk on it. And it'll be an hour, and it'll probably be much more applied than this is. But this is kind of the abstract stuff. So in a second, or maybe in 20 or 30 minutes, we'll talk about monads and how they come from junctions and how they go, how they're related, and comonads. So junctions always have monads and comonads associated to them. And that's where they kind of come from. So this stuff is relevant if you want to know what monads are. So an adjoint pair, L and R are going to be called an adjoint pair of functors, or an adjunction. L goes from C to D, and R goes from D to C. And L is called the left adjoint, and R is called the right adjoint. And the reason for the left-right nomenclature is that when I write this property that adjoints have, L is going to be on the left side, and R is going to be on the right side of this thing. So what does it say? It says, you have these two categories, you have two functors back and forth, this translation system, this dictionary, and for every C and D, I don't care if you push C forward and look in D at the maps between C and D, or if you push D back into C and look at the maps in C from C to D. Like there are no maps from C to D because C is in one category and D is in another. But if you have a functor, one way or the other, you can kind of like translate and then look for the maps. And it says that in both of them, there's this isomorphism between the maps in C and the maps in D. So this looks really abstract, I think. I mean, it's hard to get your head around what that's going to do. Like, why is that important and what's it going to do? And so to tell you that it's important, you just say, so many really, really neat things come from junctions. That's why it's good. I don't know why that's good. I just know it's good because good things come out of it. So let's do an example from currying. Currying is an example of an adjunction. The problem with it is that I need to fix a set A in advance. Like fix means pull out one and don't let it change. It's not going to change until I say stop or something. Okay, so A is fixed. And we're looking at a pair of functors, an adjoint pair, L sub A and R sub A. So since A is fixed, I could just write L and R because I don't have to mention A. But what are these functors? A functor from set to set takes an object in set and gives an object in set, takes a morphism in set, a function, and gives a function. So LA of X is a functor. It's going to take an X and return A times X. So it's like tagging. Someone called it tagging. So I'm going to tag every X with an int or with an A.
And it could be any A.
I've already fixed my A.
18, 82, 80, but just whatever some set is of numbers.
A is a set of numbers, sure. A is int, say. And I'm going to tag every X with an int.
Is X in the set on the left?
Is it in it?
No.
This is a pair type, A times X.
Yeah, but I mean, where does X originate?
So for every set X, for every object in this, I need to give an object in this. And for every morphism in this, I need to give a morphism in this.
That's what I'm saying, is the set on the left. The set
X comes from the left, let's say. So for any X in set,
But in the pairing, you're allowing X to be used more than once, like a true product, or a minute.
I'm going to give you a new set. And the set I'm going to give you is the pair type AX. A times X. What?
All combinations of A's and X's.
It's a set.
Yeah.
The set is all combinations of A's and X's. Yep. And given, I didn't tell you what it does on morphisms, but given a map from x1 to x2, I need to give you a map from a function from A times x1 to A times x2. And I just take my tag and send it to itself, identity on A, and take the function on this other side. So that's why it's a functor. You can check that that commutes with identities. If I have the identity map x to x, it'll go to the identity map a times x to a times x. And if I had to map x1 to x2, x2 to x3, and I pair it with the identity on A, I'm going to get a map from a times x1 to a times x3, so it's a functor. It's going to commute with all the things it's supposed to. So it's tag with an A. That's
A is acting as the tag.
A is acting as the tag or tagging set. There's also a functor that's functions from A to Y. So now A is an indexer or a pointer, I don't know, some place that I'm going to take any Y and give myself all functions from A to Y. That's a functor also. So how does that work? Given Y, I look at functions from A to Y. That's a type. That's a set. And that's the set I send. That's what R does. And if I have a map from Y1 to Y2, then I get a map from, so if I have a map from A to Y1, I get a map from A to Y2 by composing. So what that says is, I'm going to erase that. So it says I get a map from Y1 to the A to Y2 to the A. So if I have F, what would this map be called? I think it's like lambda A in A, F composed, what? Right. Lambda. There's some lambda for this. Lambda A, lambda F, F, lambda G, F composed G of A. I don't know, something like this. This doesn't type check, but does this make sense, or do you want me to do this carefully? Can someone say what this is?
It's circle.
It's circle.
Yeah, function composition.
It's function composition.
Yes. It's dot.
It's dot. Does that make sense? Given a map from Y1 to Y2, I will give you a map from function type A to Y1 to A to Y2 by dot. And that's going to commute with identities. If I gave you the identity function here, then given an A to Y1, I will get back the same A to Y1.
So just to be clear, the R will end up mapping back to a set of
It's going to take a set
of functions.
and gives you a set. But a set of functions is a set.
Right. Yeah.
Yep.
Okay.
Yep, that's right. And so,
No.
You don't end up in the same place.
But they look like
oh, these are not inverses. So adjunctions are not usually inverses.
they look like they are.
Well, let's check. So suppose I have x, and then I multiply by a. So if I take LA of x, and I take RA of that, that's going to be x times a, or maybe I said a times x, but forgive me, to the a. That's functions from a to a times x, which I think is state sub a, state ax. State ax. I don't know. I'm trying to translate into your world, so if I'm not doing it, then I'm not going to think. It's this thing. It's functions from a to a times x. So if I had an a, I'll give myself a new a and an x. If I was
Is it the same A, so you're passing it through? Or
same a. This a is fixed.
Well, I mean like the same instance of A, or same type, so you could basically have an updated state. That could represent updated state plus some result.
Same element of a, yeah, it could be a new element of a.
Got it, okay.
Yeah, so I think a lot of times Haskell programmers write a to, they talk about a, they like the type class former thing and like the function that you implement like has the same name kind of, or something like this seems to happen that makes like this confusion in the way that I hear what you're saying. But anyway, yeah, if you start with an element of a and you could get a new element of a.
It's more like
Reader? This is state. This is going to be state. It's going to be state. A.
Because basically you pass in the state, it changes something, and you get something out of it.
Yeah. And LA of RA of x is going to be x to the a times a. Yeah. Right? I just did one and the other. So this is certainly not X. Neither of these is the identity, right? They're really far from being the identity.
I get that, but what I don't get is when you get back to the side why it's still set.
Oh, because this is a set. If I have any set X in A to the X is a set. It's a function type. And if I multiply that by A, I get a set. So this is a set.
Not
It's-
necessarily the same elements.
It's certainly not the same elements. It's a lot bigger.
All that stuff in the set on the left.
Right, so it's just going back to the same category.
It's coming back to the same category. It doesn't go back to the same example of set. It doesn't go back to the same object. Yep. So if these are supposed to be adjunction, if these are supposed to be adjoint functors, then they need to satisfy something. It's not just a map left and a map right. It's something else. And that additional thing is that HOM in set, meaning the set of functions from L of A of X to Y, is in bijection with, there's an isomorphism between HOM and the other category, which happens to be the same category. HOM in set from X to RA of Y. And what this isomorphism says, if you write it out, it says that a function from X times A to Y, that function type, is the same thing as functions from X to the function type Y to the A. Oops. Yep. And that's currying. It says if I have a map from X times A to Y, it's the same thing as a map from X to functions from A to Y. That bijection between these two sets is currying. You can go back and forth, and we talked about this in the first 2-hour slot, I think.
But isn't that an isomorphism? Because
This is an isomorphism, and I guaranteed it would be back here. It says I can look at it in two different ways. I can regard it in two different ways. I can regard it as a two-element function fixing this A, or one element, yeah.
you said the bijections don't make an isomorphism.
So this is an isomorphism,
Yeah.
but that doesn't mean that if I go around trip, that I get the same object I started with. I get a very different object, but when I translate something across using the L functor, and then look at functions to Y, it's the same thing as not translating it, but looking at functions to the translation on the R functor. So as confusing as that statement looks, the fact that X times A to Y and X to Y to the A are the same might feel much more reasonable. I hope. I don't know.
Basically, the composition of those three would not be
The composition will return you this or this, respectively.
This is where I wish that there were more examples. You're well, currying is uncurrying, but something else like that you'd be like, oh,
Yeah, sure. Okay, let's give another example. So, but let me go from set. This time I'm going to change the category. So I'm going to go to par. So set is the category of sets and functions. Par will be the category of sets and partial functions. A partial function is one where you don't need to give a value for every element of the first, right? It's a map X to Y.
Right.
I might write them like this or something. Like some guys in here get a Y. They always get at most one. But some things in X don't get a Y. It's kind of a map from X to maybe Y. Those are the maps in par.
Because in programming we talk about oh, you forgot to cover this one edge case, this for it's a partial function,
Right.
this for it's that. Usually.
But it's not bad if you lived in partial functions.
Oh, if you're doing
If that was your category,
okay.
then you could be all of your objects are sets. You have all these different sets. But the morphism from one to another is just a partial function. There's an identity partial function. It happens to be total. And you can compose two partial functions and get a partial function. And that's associative. So this is a perfectly good category. It's just that you have to know you're living there if you want to live there. And that's why people say it's bad, because they always live here. And so it's bad. But it's good if you're over here.
I guess the only bummer I had was that when I was thinking about other examples, I wasn't meaning car, I meant trucks and cars and
Oh.
something human.
Yeah, no.
No.
Trucks and cars. But how are those categories?
I don't know.
Yeah.
But something with life, like teaching.
Teaching,
I don't
yeah.
know, the category of teaching.
No, there is none. There is a category of love.
There we go.
But I don't know. It's good. Okay, so a set is a subcategory of par. It's a subcategory, meaning I don't want it like I'll call it just I for include. Set is a subcategory. For every set, you get a set. For every total function, you get a partial function that happens to be total. But given a set in here, given an object, I do get an object. But given a morphism in partial functions, I don't get a morphism.
What you're saying is partial functions technically can be full, because by definition
Yeah.
they're still partial.
Yeah.
They just happen to be full.
Right. So it's a subcategory.
Yeah.
Here I'm going to do +1. So I'm going to take is, for any set x, I'm going to send it to x plus nothing. If I have a function from x to y, I'm going to go for a function from x plus nothing to y plus nothing by doing x on the left and nothing on the right. So given anything in here, if it's x, I'll send it to y get by this. And if it's star, I'll send it to star. So now I've given functions left and right.
So the right function is the coproduct?
Coproduct with 1. Yep. So now Hom, now I'm going to tell you these are adjunctions, which means that Hom from Ix, for any set x, a partial function from I of x to y. So I of x is just x again.
It's basically the injection.
It's x regarded as it's just x again. Because I does nothing on objects.
It's like moving 5 from integers to floats, like you said.
Yep. There's an isomorphism between the set of partial functions from I of x to y and the set of total functions from x to y plus 1. So y, if I have a map from x to y, a partial map. So I have x and y, and this guy goes here, and this guy doesn't, and this guy goes here, and this guy doesn't go anywhere. That one goes here. Then how am I going to get a map from x again to y with the special object in it? Well, I'm going to do what I said I would do when I can. Otherwise, I'll send it to +1, the nothing. And any map from x to y plus 1, some of the guys will go into y and some will go into 1. And the ones that went to y will give me ones in y over here. And the ones that went to 1 will be the partiality, the non-totalness. They'll be the ones that don't get mapped over here.
So you couldn't do this if you didn't have that +1. You couldn't have par going back down into set. You just couldn't.
Yeah, you could send every set to itself. But right, you wouldn't know where to send.
Yeah, therefore, you
Right.
couldn't do it.
I could do +2
Well,
and always use one of them.
Yeah. But you can't do it like nothing. Like, yeah, okay.
There's only one really cool way. In fact, there's only one adjoint. The adjoint, if you fix this guy, if there is an adjoint, it's unique. There's only one thing that'll be adjoint to I, and that's +1. I said I could do +2, and you're like, no, that's stupid.
No, I didn't say
But well, no, you didn't say it. I said that.
Why is,
But it perfectly works. What?
why is +2 stupid?
Well, I'll just add this extra guy, and I'll never use it.
Yeah.
That's kind of weird.
Sometimes.
But no, I'll never use it. If I sometimes use it, it's going to make everything too hard. You'll never come up with a functor that does that.
Because you can't.
Because for every morphism, you're going to need to choose, am I going to use it or not? And they all have
You
to,
need something else to help you choose.
not only that, you need something else to help you choose because the composition formula, it won't respect composition if you're not careful. So you could do +2 and not use it, but that won't be adjoint. So this kind of fixes, just like Ev before, like the rule I told you here, when I started erasing, tells you it's like the best possible.
It's like the universal property.
Yeah,
Sort of.
yeah,
Is it a universal property?
yeah. I don't know, kind of. Yeah.
Are the objects in R functions or sets?
Sets.
Okay, so the objects are still sets.
Yeah, I might
They-
call it set subpar. I think in my notes I called it set subpar.
Okay, but the arrows between those sets are partial functions instead of.
Yeah, this might be called set subtote or something, right?
Okay, cool.
When you say that these are unique, the adjoints are unique, is that unique up to isomorphism? Or is that
Yeah,
unique?
unique up to isomorphism.
Isn't almost everything unique up to
Yeah,
isomorphism?
yeah.
Okay.
Okay, so yeah, so that's par. That's an adjunction. Do you believe it, that it works? Is it clear enough that it works? Okay.
Prove that one's the smallest or best or whatever.
How do I prove that adjoints are unique? What? So this will work. Like there is a isomorphism between these sets,
Right.
and anything else that had that property I could prove was isomorphic to +1. I didn't, and I won't for you, but
How do you prove that like +1's the best one here?
there's only
An
one.
intuitive thing?
There's only one.
Right, but you have some other things that are isomorphic to +1.
Oh, but they're like plus. Instead of calling this plus star, they'll be plus smiley face.
Right.
They're all the same. But smiley face and 1, they're not really the same. So you have to use this isomorphism, and then like the difference is just one of labeling. That's what I mean when I say they're the same up to isomorphism. It's like smiley face and 1 are the same. It's just a matter of what you call it. So there's also a functor from set to monoid. It takes any set and gives you the free monoid on it. And it's like, and there's a functor back that takes a monoid and gives you the underlying set. Actually, maybe I won't say this. It's kind of too much, yeah.
Well, see, because the way that I've always heard it is that the left adjoint basically gives you or builds up the structure, and the right adjoint is forgetful. It removes the structure.
Okay, that's not always true.
Okay,
So
this doesn't sound like that.
free forgetful, right, and neither is this one, right? Like multiply, 8 of the y is not a forgetting at all. So a lot of forgetful functors happen in algebra, for example, from sets to groups and stuff.
Okay.
Oh, I didn't start a timer at all on this one. I have no idea what's going on. So we started at 3:30?
Yeah.
Okay, okay.
What time were you done?
What?
5:30.
We're stopping at 5:30. Okay, so
So that's good to know that you don't always have to have this forgetful structure.
No,
stuff.
no,
It's
yeah.
just whatever.
yeah. This one is, it takes a set, you have a set like ABC, and you get the monoid of all lists in ABC.
We define
Can we actually do this? Because this one actually comes up in development.
It does?
Like, there's
Okay.
this huge thing about free, and I mean, this is huge. This is
Oh, okay. List
and
X,
everything with free.
that's, a monoid has a set. So you can think of a monoid as a category with one element, one object. To do that, you would take your set, put the one object, and put all the elements of the set as maps, and have the composition law just be free, meaning like if I do one then another, I'm going to call that a map too. I'm going to add not just like, I'm going to take this graph with all the elements in there, all the elements from X, and then I'm going to look at all paths in that thing, and that is the free monoid on X. But an easier way to think about it is not in terms of the category thing, but just monoids, meaning a set with a multiplication law and a unit. So for any set, I have the set of lists in that set, lists of X's. I have the empty list, and I have append, and that's a monoid. That's called the free monoid on X, meaning I didn't make any two lists equal that weren't equal. In a monoid, I could make two of these lists equal, like A followed by backspace equals empty list or something. I don't know. Like I could say I have a list of things I can do, and then some of them cancel or are equal to other things I could do.
And that's on a monoid. Like
That could be a monoid.
action.
That could be a monoid, yeah, that could be a monoid. But this is the free monoid, meaning I did the least possible thing to get myself from a set to a monoid. So I'll call this free. And U is underlying. For every monoid, M with a unit and star, I forget the unit and the star, and I just write down M.
Let's take an example. If you had a set on the left, like going to that first one, like take a set, 1, 2, 3.
Yeah.
What would be the monoid?
The set of all lists in 1, 2, 3,
So what would that be?
with the empty set and append.
Like, but like, can you enumerate them? Because this is where I get like,
Okay, so there's 1, 2, and 3, 1, 1, and this guy.
any combination that makes use of any subset of 1, 2, and 3.
Any list. So I thought
So it'd be
list.
like 2, 2, 2, 2, 2, 2, 2.
Yep.
Oh.
So I thought a lot of this time that when I said list A, you knew what I was talking about. I guess that was wrong. I apologize for that. So list A means the set of all lists in A, meaning lists of A's. What? No. So the power set would not include this. The power set is all subsets of A.
Which is, you can't have duplicates, so 1, 1, and you, like.
In lists, you can.
1, 1, but in a power set, you couldn't, because there'd only be 1, 1, or 1.
There'd be a single one.
There'd be a single 1, 1.
No, single one. Single one.
Single one.
Oh, really?
Well, because it's a set, so you can't have duplication.
Right.
So a power
So
set is
when I say list, I mean the set of all lists you can write where the entries in those lists are elements of X. Okay. So if I said there's a map, so if I said list of
2 to the power of the side.
this guy was isomorphic to the naturals, would you believe that or think it was false?
Sure.
List in star, so it'll be a list where every element, every entry in that list, every entry in that list is going to be star.
Yeah.
So that list will only tell you a length.
Yeah.
Okay.
And because star could also be smiley face, or you could put that, like a lot of people put a 1 right there in that little squiggly. Yeah.
Okay. So,
It's a business for that.
so would you believe, I don't know if this is going to be useful, but would you believe that Hom in monoids, a monoid homomorphism from, let's just call this free of X, the free monoid on X, to M for any monoid. What this means is I have a monoid map from free X to M, meaning for every list of X's, I get an M. The empty list is sent to the unit of M, and concatenation of lists is sent to multiplication in M. The set of all ways of doing that is exactly the same as the set of all ways in set from just looking at X to the underlying set of M. Like if I have ME star here, it's just M. But it's true.
What does underlying there mean?
You have the structure of a monoid, meaning you have natural numbers with plus or with times. Forget plus and just look at M, the natural numbers. That thing doesn't know about plus or times. It's just the natural numbers. And that's what U of M means. Forget the structure of the monoid. So it says, for every X, if you give me, for every element of X, give me an element of your monoid. Then I will be able to take any list of X's and turn it into an element of your monoid by just taking that list of X's and multiplying together all those M's. Does that make any sense? Yeah. So given an element in this Hom set, that's a map from X to underlying set of M. Then I need a map from list of X to M. And it's basically going to be a fold. I'm going to fold using M's times an E. M has a times and an E. And I'm going to fold with E and times the list of X's to get an M. And doing that is going to work correctly with respect to the empty list and the append. So it's not just a fold, it's like a really nice fold. I don't know what to call it, but it's a fold with this, it's kind of associative or something. Yeah, it's a fold. Anyway, but given a map, if I have a map that takes lists to M's that happens to work with append, like if I fold up a list and fold up another list, it's the same thing as folding up the append of those two lists, then I could just think of that as a map from X to the underlying set of the monoid, because all I really need to understand is what that thing does on the one element list, on one element lists, and I'll know everything. Because I can just take any list, think of it as an append of lots of one element lists, and append them all and map. That's the same thing as mapping and appending, and so this is true.
And then the
Is the
underlying
upshot.
set of M is the list of X's.
The underlying set of M,
Is the list of X's.
no, the underlying set of M could be any monoid. It could be, yeah, M is any monoid.
Oh.
So if I can, yeah.
I'd like to know terminology, like how you speak to this. So you would say, I think we're calling U the forgetful forgetful functor. Like, could you say this in English so I know how to talk?
Yeah, yeah. I've defined, there's two categories on the board, set and monoid. I've given you a functor free from set to monoid. I've given you a functor u from monoid to set, and free is left adjoint to u, and u is right adjoint to free. And it just so happens that u is a forgetful functor because it forgets some structure, but, right. Yeah.
When you say forget structure, do you mean it loses the function?
It loses the times in the e. So if I give you the natural, let's say I have a monoid over here. I'm thinking of one. And then I forget it and I give you the naturals. Which one was it?
You don't know.
It could have been naturals with plus and 0, or it could have been naturals with times and 1. So I've forgotten some structure, but I still gave you back a set.
I think I understood. So because we use this word free kind of in other contexts, could we talk about free monoids and free monads?
So free has a notion in category theory. A free functor from one thing to another thing is left adjoint to a forgetful functor, and it always means that. So,
by definition.
well, I mean, I'm not sure if I can really give a definition. I think I can, but I'm not sure.
Yeah,
but it's pretty close. Like, there's pretty close to a definition of free, and yeah. Yeah.
How does also, because the other thing that free comes up coming as a huge topic, and free and co-free, and how those relate, and how,
I don't know any examples of co-free. It's different free? That's funny. Okay. Oh, okay, right. Do you guys want a chance to talk to your neighbor about stuff? Not?
No, let's go. Keep going.
Let's keep going. Okay. So, for every adjunction, so we had this adjunction C, D, L, and R. And we have Hom, I think I just erased what I wanted. Hom and D from LC to D is isomorphic to Hom and C from C to RD, no matter what C and D you pick.
And those little d's are exempt element of big D.
Yep. Now, an interesting thing is that L of C. Do you guys mind LC? Some people want me to write L parenthesis C. Fine. Okay. LC to LC. LC is a D. So I can write this. It makes sense. And there's an identity in here. Identity in LC is an element of this. It has to be. And not only is it one, but it's one that I've given you in advance, and you know what it is, and it's really an important, as trivial as it is, an important function. Well, this is isomorphic to Hom in C from C to RLD C. Isn't that true? I just took D and replaced it. Right? I just substituted LC in for D.
What's the order of that? You're doing C, you're doing L on C, then R on C.
Yeah, sorry. This is R of L of C. Yeah. Yeah. R of L of C.
It's unambiguous though, right?
Wait, L of
Type.
C,
Yeah. If you're.
Or
Yeah.
work on L.
Right.
Wait, is it L of C, L of C the same object?
They're the same object.
But that's not the same object, because I thought.
Right, but I told you that for any D, you could plug it in, any D in D, you could plug it into this formula and get a fact, get an isomorphism.
Okay.
And so the D I chose was LC.
Oh, if you chose that.
Yep, if I happen to choose this one, I get this. Which means that the identity in C, which is this particular element that must be in here, goes somewhere here. I don't know where it goes, but it goes somewhere, and I always can touch it. Like it doesn't. There may be a billion things in here, but there's one I can touch, because that's part of the definition of category, is that I have an identity, that self thing. And so what that means is that I have a map from C to R of L of C, just given. And it's called the unit. People often write it like this, like eta. But it's going to turn into return. Like if you know what a monad is.
Oh, pure. That's how you inject it into, you put it into the structure?
Yeah. So what do people call it for monads? Return and bind or not? Okay, this is return. I'm going to use return and bind because that's what I've been told. But so this is going to always be return. And there's also one on the other side. There's also hom. There's also in here, there's hom in C from R of D to R of D for any D. And that's isomorphic to hom in C from LRD, just substituting to D. Just substituting up here. And this says that given my unique identity on RD, I'm going to be able to get some map from LRD to D. And that's called the co-unit and is often written epsilon.
What's the name of that other squiggle that you did for return?
Eta. ET.
Is that an N?
It's like it's the end with the long tail.
Yeah.
Oh, and that's a subscript C.
And that's basically
Eta
extract.
subscript C.
That's basically extract right there.
I don't know.
Co.
So the thing is that, right, so I would call that thing co-return, I guess. It's called the co-unit. This is called the unit in category theory, and this is called the co-unit. And these satisfy these interesting laws. But I don't know if I want to say much about those. Oh, that's true.
Why are they fascinating? What are the fascinating laws of
You want to see that?
or
Okay.
at least mention them?
So I like to think, some people write a monad, they write a little that thing in there. And I don't really like that very much because it doesn't tell you much. It always points weirdly towards the R.
Isn't that bottom, the symbol for bottom?
Yeah, but if R was on top here, they'd write it with a top. So they like, this thing is,
It's like that turnstile thing. It's like
Yeah.
R infers. Or
I guess, but I think it's nicer to write that.
Yeah.
And the reason is C, D, C, here's L and R. And this is, I write equal sign for the identity on C. It's a functor. That's a functor, that's a functor, that's the identity functor. And this goes like this. I have a functor from identity on C to RL. Sorry, a natural transformation, eta. So eta, this guy is a natural transformation. Just like I drew before, I draw like the two functors, I draw a little 2 arrow between them. Right, I would draw C, and I draw a little 2 arrow. That's the same type of thing. It's going from this functor to this functor, that composite. And it's a natural transformation, meaning if I plug in any x, I have eta x, taking x to RLX. And it's kind of natural. If I have a map from x to y, I get a map from RLX to RLXY, RY, and I get a naturality square there. So this is a natural transformation, but that's fine. And there's also one, if I have C, and I have D, and I do R, and I come back with L, then I get epsilon there.
Is RL of C in D or is that in C?
Let's see. If I do L of C, I land in D. If I do R of that, I get back in C.
So what's the example of C in this case? Because like basically isn't that you're sticking some normal value into a monoid or into an something.
So let me do this, then we'll go to the examples. So the monad laws are that if you kind of do this 3 times, if you do L, then R, then L, and you do these natural transformations, that's kind of the same as just doing L. I don't know if this is, I don't think this is an abstraction. It's kind of neat, but doing this, you can start on the identity on C and do L. Then you could kind of go LR, L, and then you could, by this natural transformation, then you could do L, and you get a map from L to L at the end of the day, and that's the identity, natural transformation. Kind of weird, but it's true. And same for the other way. These are called the triangle laws. Triangle laws. Okay, so let's do some examples. So soon we'll be able to use the return or the unit to be the return, and the co-unit is going to help us get join for a monad, which in turn will help us get bind for a monad. So I'm going to erase this because it's not that important, and I want the space before I erase the example. So the first example I gave was currying. I said you have a map from set to set, and you have times a, and you have blank times a, and you have blank to the a. What is the return? What's the unit? It takes an x to RLX. But in this case, L of x was x times a, and R of x times a was x times a to the a. So unit is a function, not one of these guys, but like an actual map, an actual program that takes an x and returns a map from a to a times x, like a state thing. And what is it going to be?
You erase the other ones just because you were kind of like showing how they transform as they go. That's why you're erasing them, right?
Why did I erase what was here?
Yeah. No.
Because I want to get.
No. Like literally, you used to say RLX.
Oh, as I went, yeah. So this one's the R, and this one's the L, and this one's the R. So it's kind of like this direction. I don't know. Yeah. Yep. So this is going to be the eta, and there's also going to be an epsilon from a times x to the a to x. So suppose you had an x, and you wanted to take a function that took an a and gave you an x and an a. What would you do to an a?
You would just cross it with, just pair it up identity.
Yeah, it feels like identity, and the reason is because it came from the identity. That's where this thing came from. But it kind of like unwraps a lambda in a weird way. It takes an x and gives you a function from a to a times x. It like wraps pairing and lambda somehow together. But the reason it feels, probably, I don't know. But the reason it feels like the identity is because it came from the identity. And what about, but this one might not feel as much like it. I don't know, we'll see. So what would you do if you had an a and a map from a to the x and you wanted an x? Yeah, you apply. So this is ev. And ev and identity, I guess, are the unit and co-unit for the adjunction here. Whatever that means, there they are. So let's do it for this one. Maybe with your neighbor, try to figure out what the unit and co-unit are for this. Is that are you ready to do that, or do you need to ask something first? Let's ask, are there any questions before you are ready to do this, and then maybe this one also? Yeah.
I just need a reminder of what that is.
Okay, let's see what these are. Category of sets with partial functions. Meaning the morphisms here can be partial, but they have to be total here. This thing takes a set and returns itself, takes a morphism, returns the partial function that happens to be total. This thing takes a set with a partial function, takes a set and adds 1. Takes a partial function and returns the thing that like sends every missing data to the new +1 type. Okay, so with your neighbor, figure out what unit and co-unit are for this adjunction.
Where does unit and co-unit, kind of like in this diagram, where does unit and co-unit, kind of where would you write that?
It's like set. There's unit.
And then the co-unit is where?
So left just takes us from set with partial. R takes us back.
Okay, what does this say? Given a set, I could either look at it as itself,
Yeah.
or I could multiply it by a and then take it to the power a.
And this is literally saying this is the thing that enables me to inject it into this new thing.
Yeah.
And then simultaneously, I can say this is the same as it's, this new thing is the same as that, or I could take it back
And push it forward using function type, and then multiply it, and then evaluate. So these are the unit and co-unit.
because the co-unit is actually taking this. I mean, you're drawing it this way, but isn't it kind of actually that way? Which co-unit takes it from this side and sticks it.
No, it takes you from this to this. Look, on this guy looking here, here's x starting there, and if this is a times x to the a, and it goes to x.
Oh, because this is x here.
X is in there, yeah.
So I wanted to say on this, like, at least a lot of times the laws are really important to us. Just in case you're curious, like a lot of times we're like, is this a monad? Like, it looks like a monad.
I will get to monads, and then I'll talk about the laws.
Yeah.
I will talk about the laws for a moment.
Okay.
Yeah.
Just letting you.
Yeah, okay.
Now, like, so sometimes I'm like, it looks like an injunction.
That's how we're getting.
But how do I know?
Yeah.
So understanding the laws, I don't know, it's interesting.
Okay.
This is a little, I'm slowly getting it.
Yeah.
It's awesome.
Okay, great. All right, one more minute.
One more. Oh, crap.
Okay, two to do.
Yes, better.
So what do we just that?
I'm asking you, what are the unit and co-unit for this? The unit is going to be mapped from set to set, and the co-unit is going to be mapped from par to par. What do they do?
R adds 1. Okay. And L doesn't really do anything. So we really got X plus the sigma thing. That's our error. So eta just snaps X to X plus that's our unit. And then epsilon is L R of D. Or I guess Y, our partial set, partial function set. And that maps back to Y. So R of Y is just as plus 1.
Get is like, if this is really, if this
L again
C
is
goes to RL of C, but
L gets
this
that's the partial function.
is in C.
So it's the same.
I don't
C is
get
over
that.
here.
So eta goes
Yeah, so this is
Y
C,
plus
but then your
RL
point is this C, but going here, I take a C, and I do it to R L of C, which means I'm back in set.
Yep, and I have a map.
But I don't get that because isn't the whole point about a unit is that I'm taking like an integer and sticking into a monoid on the integer. I'm
But it's still a-
something else, so I'm not in the set. I'm in
I am.
something
Yeah, I am though.
different. Why?
This is a set, isn't it?
But isn't it?
It's a different set.
It's a different set. So like,
A different object in set. Let me start again.
yeah, because it's kind of like when you stick it into like a monoid. Isn't a monoid totally different?
Yeah. But this will always land you back where you started because you went forward and back. It'll always land you in the same category you started with.
So let's say if I start with int, it might take me back to an int.
No, this is the category of sets. It'll take you to.
Category of sets.
It'll take you to the same category. No, it's C, but
Okay, so it's not.
let's start again.
Which is a type. It's a category of set. Okay, I'm with the
Yeah. But you can ask.
mapping that thing
Okay, so questions?
back to the thing you started with.
Did you guys have questions when you were working on this that you needed clarification on? Any questions? Did anyone get it? Yeah, did you get it for partial?
He's got on this.
Can I stop you? It's okay. For the partial one, you got it or no? Okay, what is? Okay, that's okay.
So it maps to maybe from Haskell. So the unit is just, and co-unit is from just.
Is that right? So the unit goes from, so this was what was for that one over there. For this one, we go from a set to that same set plus 1. And you're saying that's just. That sounds right. Yep. And for the other one, you start with a set, and you again go to x plus 1.
You start with X plus 1.
You start with X.
No, you start with a set over here. Oh, right. The other one goes from x plus 1, you're right, to x. So you go from this back. So I need a map from x plus 1 to x. And what is it?
From just.
But this is a partial function, luckily.
Which is okay, because you're in partial land already.
Right. So I get a partial function from x plus 1 to x that takes everything in x and sends it to itself and sends 1. Doesn't act on 1 at all. Yeah. Okay. That's the answer.
Just takes it is the unit.
X is the unit,
Okay, unit.
and this is the co-unit.
Get back a partial function.
Yeah. You get back a partial function because this one's supposed to take place in D, in par. This one's taking place in set. Yeah.
So, the x plus 1 to x, are we losing information by throwing away everything in math for 1?
This is a function, a partial function, that takes anything in x plus 1 and gives you something in x, but it misses one. It's partial. Are you throwing away information? Why do you say that?
Because then anything that maps to 1 now doesn't exist anymore in X.
What do you mean map to 1, though? This is just a set. I just have a set, and that's all I'm saying. So there's nothing mapping to it unless somebody else mapped to it. If something else mapped to it, then anything that mapped to 1 is thrown away. But that's just saying that, like, given a map from y to x plus 1, I get a partial map to x. So it's a perfectly fine thing to do. And you do throw away something, but you kind of throw away just enough. I don't know. It's an adjunction, so I know it's going to behave in a kind of nice way. It's going to give us a monad. Some people might already guess what monad this is going to give us. And yeah. Yeah.
I don't get how you say that unit takes you from x, whatever x is, and then you end up back in the same category, but just takes you from x into maybe x.
But that's the same. They're both living in Hask.
Maybe it's just the +1.
Maybe it's +1.
So your point is, because it's still in Hask, we're still in the same category. Because
Yep.
literally, we got any.
This one is what I was calling set, and this one's living in par. But both of these guys are in par. Both of these guys are in set, and that's So let's do the last one. Yeah. Let's do set and monoid.
Would it work or would?
Well, let's see what happens. Okay. So set and monoid. Did anyone do this one?
X and maybe.
We tried.
Okay. So what happens? What's the unit? I need a map from a set x to. If I apply free, I get list x with some stuff. And then if I forget the stuff, I just get list x. Whoops. So what's the unit from x to list x? Yeah. I'll just write a singleton. And that's kind of like the return, at least for me. I think it's the unit. And now I need to map a monoid map. So this is in set. And now I need a map in monoid. I need a monoid homomorphism. It's not only a set map, it's not only a function, but it also keeps track of the extra stuff, the list, append, like all that stuff. I need a map from that to, list of M.
Because on the left you've got the monoid.
Co-unit.
Lifting it back.
Yeah, I'm starting with a monoid. I'm applying U.
On the left side there, yeah.
I'm applying U, and I'm taking the free. When I take U and when I take M, I forget its structure, its times and its plus, times and its unit, and I just think of it as a set. Now I look at list of elements in M, and I give my own version of a plus and a unit for the monoid.
Oh, that's co-unit?
This is going to be co-unit. And what does it do? If I have a list of M's, so what's your favorite monoid?
Some.
The natural numbers with plus, right? Is that just a good one? Okay, so let's say I gave myself a list of natural numbers. Where should I send it under the co-unit? So let's say M is the natural numbers with 0 and plus. Then what should I do with this thing? I should fold it up into 17.
By the way, that could be 3, 3, 8, 1. You could have multiple 3s,
Yeah.
right? Okay. So the co-unit is
Mental math. What do you say? The
so
co-unit
is pulling it back into the numbers.
Yeah,
the natural
right.
numbers.
And I always can take my M and take any list of elements in M, and fold it back up into an M. And that is the co-unit.
That's how you forget it.
Yep. Yeah.
M is the actual monoid, or M is just the
Yeah.
underlying set?
M is the you're right. M E times. This is going to be a monoid map. It's going to send any list of M's to an M, and that's going to send this one to E and append to star. And how's it going to work? It's going to take any list and multiply up the elements given M. And if I give you the empty list, I'll just multiply no things together to get E.
I see.
And if I append two
so
lists,
rather
yeah.
than using the append operation on the elements, you're just doing the add or multiplication element on all the elements.
Yeah, but this is a monoid homomorphism,
Right.
meaning that if I take two lists and append them, and then multiply each. And then multiply, it's the same thing as appending, well, whatever.
I got it.
Yeah. Append then multiply, the same thing as multiply then
You're
append.
doing addition, so in this case, the E would be the 0 and the
Yeah.
star would be the plus.
Yeah, this would be 0 and plus.
Literally fold map.
This is fold, yep. Fold that happens to be a monoid fold. No, it's not. So for example, if I there's a fold map like minus with 1, right? So I take any list, 3, 3, 2, 8, 1. Oh,
Fold map actually takes the monoid.
okay, thanks. I was thinking of fold right, I guess.
No, fold map is
Fold map is with the monoid.
Okay.
Is that a,
When I think of fold, I think of just something that I can, if I have an empty list, I get a value. And if I take a value and something I can like kind of keep folding in. And I could take the empty list to 1 and take it and just keep subtracting. And that's not going to be a monoidy thing to do. So I don't know whether I'm agreeing with you or not, but
Fold map is just a special.
fold map, great.
For the monoid.
For the monoid case. Okay, good. Yeah.
So you said we have monoid homomorphism.
Yep. This is a monoid homomorphism from here to here.
Does that mean that if we have categories of monoids, there's a junction between monoid and homomorphism?
What? I didn't parse the.
If we have,
This is the category of monoids.
so is there a junction between monoids, are monoid homomorphisms also junctions as homomorphisms?
I don't think so, but I don't really know what you're asking. Yeah.
So, I would be helpful if you were to repeat what this is an example of.
Okay. The whole thing we're talking about in this part of the talk is junctions, which there is a whole talk on Saturday. Junctions go between two different categories. There's two different functors, one left and one right. And there's an isomorphism that says you can translate left and look at maps, or you can translate right and look at maps, and they're the same somehow. C to RD versus LC to D is the same. But then given that fact, you get these weird special maps called the unit and co-unit. And those are going to be helpful in defining monads. For example, the return and bind or return and join of a monad, and whatever the opposite things are called for comonads. Return and unit and co-unit are useful operations, but we haven't talked about why yet.
are those only occurring if you're on the same, if C and D are the same category?
No, they always work.
Even if they're different categories?
Yep,
Okay, got it.
yep. And what we did was we said we had three examples of adjunctions going in. One was from set to set. It's multiplying by A and then power A. And that the unit and co-unit turned into a kind of identity-like thing and a kind of evaluation. We also had an example of sets and partial functions, set versus set with par. And in that case, the unit was just from x to maybe x, and the co-unit was the partial function from x plus 1 to x that just doesn't put the plus 1 anywhere. And we also had functors free and underlying from set to monoid, and we gave the unit and co-unit for those two. One was singleton, and one was fold up a list using the monoid. So singleton is an important way to go from types to their lists, and folding is an important way to go back. And those both show up as the unit and co-unit from this adjunction. So adjunctions always give you like familiar, they often, or maybe always, give you familiar ways of, they always give you familiar things. And when I say always, what I mean is if they didn't, they'd become familiar because you'd start thinking of them as cool. Yeah.